Hello, everyone. Welcome to the Analog Electronic Technology course. Today, we'll explore the Class B Complementary Symmetry Power Amplifier. Common drain or common collector circuits are both voltage followers. Although their voltage gain is approximately 1, they provide a high current gain and therefore achieve significant power gain. In addition, they have a strong load driving capability, making them well suited for power amplification applications. This is a common collector amplifier using an NPN BJT. Under static conditions, the transistor has no quiescent bias current and operates in Class B mode. When a large sinusoidal input voltage is applied, the transistor conducts only during the positive half cycle, producing emitter current and delivering the positive half of the waveform to the load. During the negative half cycle, the transistor is cut off, and the voltage across the load is zero. This shows that while Class B amplification significantly improves efficiency, it only works during half of the input signal cycle, resulting in severe nonlinear distortion. In the PNP BJT common collector amplifier, the transistor conducts during the negative half cycle, allowing the load to receive the negative half of the signal waveform. By combining these two circuits, T1 and T2 conduct alternately, handling the positive and negative halves of the signal in a push-pull configuration. As a result, the load receives the complete signal waveform. This is known as a Class B dual-supply complementary symmetry power amplifier. Next, let's take a look at the power, efficiency, and other performance metrics of this circuit. Since the transistors operate under large signal conditions, we use a graphical method for analysis. We know that transistor T1 operates during the positive half cycle of the input signal, and its current voltage waveform appears as shown in the graphical representation. T2, being a PNP transistor, operates with a negative supply voltage, and its characteristic curves lie in the third quadrant. If the collector current of T2 flows out of the collector as indicated in the circuit diagram, then the coordinate axis for IC2 points downward. Because both transistors have zero quiescent current in the static state, their Q points coincide. This allows us to combine the characteristic curves of both transistors into a single diagram. In this case, the load line passes through the VCC point and has a slope of -1/RL. When the two transistors are perfectly symmetrical, the diagram clearly shows the maximum linear operating range before the operating point enters the positive or negative saturation regions along the load line. Here, VCES refers to the saturation voltage of the transistor. The output power is calculated as the product of the RMS output voltage and RMS output current. When the output voltage reaches its maximum undistorted amplitude, the maximum output power can be achieved. If the saturation voltage is neglected, the maximum output power is approximately equal to the square of the supply voltage divided by twice the load resistance. The power dissipation of the transistor can be calculated by finding the instantaneous power of the transistor and then averaging it over one period of the sinusoidal signal. Since the signal is sinusoidal and each individual transistor only conducts during half of the signal cycle, the power dissipation of a single transistor can be calculated using the following integral expression. The total power dissipation of the two transistors is twice that of a single transistor. If we ignore the input signal power, then the power supplied by the power source equals the sum of the output power and the power dissipated by the two transistors. When the saturation voltage is neglected and the output voltage reaches its maximum value, we can determine the maximum power supplied by the source. By comparing the output power to the power supplied by the source, we can determine the efficiency of this type of power amplifier. When the saturation voltage is neglected and the output voltage reaches its maximum value, the maximum efficiency of the circuit can be calculated to be approximately 78.5%. It is clear that these power metrics are functions of the output voltage amplitude. Except for transistor power dissipation, all other metrics are monotonic functions of the output voltage. By finding the extreme value of the transistor power dissipation, we can determine the corresponding output voltage. Comparing this with the maximum output power gives us the relationship between maximum transistor dissipation and maximum output power, one of the important criteria in selecting power transistors. The relationship between output power, power supplied by the source, and transistor power dissipation versus output voltage amplitude can be represented using curves. Note that both the horizontal and vertical axes of the graph are normalized with respect to the supply voltage and the maximum output power, respectively. Based on the design requirement for maximum output power, as well as the supply voltage and load resistance, we can determine the selection criteria for power BJTs. The maximum allowable power dissipation of each BJT must be greater than 0.2 times the maximum output power. The maximum collector emitter breakdown voltage must be greater than twice the supply voltage. The maximum collector current of the BJT must be greater than the maximum current through the load. From the analysis above, to achieve maximum output power, the parameters of the power BJT must meet the following conditions. The maximum allowable power dissipation, PCM, of each BJT must be greater than 0.2 multiplied by kΩ. When T2 is conducting, VCE2 is almost equal to 0, then VCE1 reaches its maximum value, which equals 2 VCC. Therefore, the selected power transistor should have an absolute VBRCEO rating greater than 2 VCC. The maximum collector current through the power BJT is VCC over RL, so the rated ICM of the chosen BJT should not be lower than this value. After this lesson, you should be able to understand the characteristics and classification of power amplifiers, and master the operating principle and performance calculations of the Class B Complementary Symmetry Power Amplifier. Summary: 1. Power amplifiers operate under large signal conditions, and are typically analyzed using graphical methods. The main focus is on how to maximize output power and efficiency while keeping distortion within acceptable limits. 2. Compared to Class A power amplifiers, the Class B Complementary Symmetry Power Amplifier has the major advantage of higher efficiency. Under ideal conditions, the maximum efficiency can reach approximately 78.5%. 3. When selecting power transistors, special attention should be paid to their maximum power dissipation, maximum voltage rating, and maximum collector current. That concludes our lesson on the Class B Complementary Symmetry Power Amplifier. See you.